Hey, welcome to The Explainer. Today we're diving into a really cool idea in machine learning called AdaBoost. We're going to find out how a team of, well, pretty simple models, none of them geniuses on their own, can team up to create something way more powerful than any single expert. All right, let's get into it.
So, picture this. You've got a massive exam coming up, and you pull together a study group. The catch? Nobody in the group is a prodigy. So how on earth could this team of average students work together to beat the smartest person in the class? Believe it or not, this is the exact kind of problem that boosting algorithms were born to solve. You see, the secret sauce isn't just studying together. It's how you study. The real key is to systematically learn from each other's failures, to just relentlessly focus on the mistakes. And we're going to use this idea of a smarter study group to really understand one of the most important algorithms ever developed. Okay, so here's how this smart study method actually plays out. Student number 1 takes a practice test. Then we look at every single question they got wrong. Now, for the second student, we don't just hand them the textbook. We say, look, these specific questions, these are the killers. You need to master them. After they take the test, we do it all over again, highlighting the new set of mistakes. With every single cycle, the group's attention gets sharper and sharper, just zeroing in on the toughest material. That iterative focus, that's everything.
Now, this whole study group idea, it's not just a cute analogy. It's pretty much the exact blueprint for a very real, very powerful algorithm. So it's time to formally meet AdaBoost.
So AdaBoost, it stands for Adaptive Boosting, and that name is perfect. Just like our study group, it takes a bunch of simple models, we often call them weak learners, and it combines them one after another, sequentially. And that word, adaptive, that's the real magic here. Each new model adapts by paying way more attention to the things that all the previous models messed up.
Okay, but how does an algorithm actually focus on mistakes? I mean, what does that even look like in practice? Let's peel back the layers on this secret learning method. It all boils down to this really clever system of weights.
All right, step 1 is something called sample weighting. At the very beginning, every data point, every practice question, starts with the same level of importance. But after that first weak learner gives it a shot, AdaBoost goes in and increases the weight or the importance of every single sample it got wrong. It's basically telling the next learner in line, hey, you, pay extra attention to these problems right here. They're the tricky ones.
Next up, you got to realize that not all learners are created equal. After each one is trained, AdaBoost gives it a grade. We call this a learner weight, or alpha. And this grade is based purely on how well it did. The models that make fewer mistakes are seen as more trustworthy, so they're given a higher weight. They get a louder voice, more say in the final decision. And this chart right here, it shows you exactly what I mean. On the left, you've got a model with a high error rate. It gets a tiny learner weight. Its opinion is basically a whisper. But on the right, a model with a super low error rate gets a huge weight. It becomes the trusted expert on the team, and its vote is the one that really counts. And that brings us to the final step. The weighted vote. When it's finally time to make a prediction, every single weak learner gets to cast a ballot. But the votes from those super accurate, high alpha learners, they count for way, way more. So it's not a simple one model, one vote democracy. Nope, this is a meritocracy, where the best performers get the most power. So let's recap this whole workflow. It's really just one powerful loop. You start with a clean slate, equal weights for everything. Then you train a model, you grade it, and you give it a say. And the most important part, you then highlight its mistakes for the next model. It just keeps doing this over and over, and each cycle makes the team a little bit smarter, until you get that final weighted vote that combines all that focused learning. It's simple, it's sequential, and man is it effective. Okay, the theory sounds great, right? It's elegant, but the real question is, how does AdaBoost actually perform out in the wild? Let's take a look at where it really shines, where it kind of struggles, and how it stacks up against its main rivals.
Chances are you've run into AdaBoost and didn't even know it. You know that little box that shows up around your face on a digital camera? AdaBoost was one of the key breakthroughs that made that possible in real time. It's also working behind the scenes in spam filters, systems that detect financial fraud, and even in scientific fields like bioinformatics. Its impact is pretty much everywhere.
But like any tool, it's not perfect. It has its pros and cons. AdaBoost is absolutely fantastic at reducing what we call bias. In simple terms, that just means it's really good at finding the true underlying patterns in your data. But here's the catch. Its greatest strength is also its biggest weakness. That laser focus on every single mistake makes it super sensitive to noise. If you have a few data points that are just plain wrong or mislabeled, AdaBoost might obsess over them, thinking they're super hard problems, and that can actually hurt its overall performance.
So how does this stack up against another big name in the game, bagging? Well, in many ways, they're like two sides of the same coin. As we've seen, AdaBoost trains sequentially, one model after another, to crush bias. Bagging trains models all at the same time, in parallel, to reduce variance, which just means it keeps the model from freaking out over tiny changes in the data. Think of it this way. AdaBoost is one collaborative study group. Bagging is like having 10 different study groups all work independently, and then you just average their final scores.
And what about its younger, more famous cousin, gradient boosting? This table breaks it down nicely. Let's look at that weight update row. We know AdaBoost works by changing the weights of the samples, the questions, to focus on mistakes. Gradient boosting takes a more direct approach. It literally tells the next model, hey, the last guy was off by this much. Your job is to predict that error and fix it. This method is generally more flexible and powerful, but as you can see, that power comes at a cost. It's just a bit more complex to get up and running.
All right, we've gone through the theory. We've seen the real-world uses. We've looked at the competition. Now let's wrap this up with the most important takeaways and see just how easy it is to put this thing to work yourself.
And you know what the best part of all this is? After all that theory, all that math, actually using it is shockingly simple. All of this power is right at your fingertips in just a few lines of code. If you're using Python and the scikit-learn library, which is super common, this is basically all you need to do. First, you just import the AdaBoost classifier. Then, you tell it to .fit your training data, which is where all the learning happens. And finally, you use .predict to get answers for new data. That's it. 3 steps, and you've just used one of the most foundational algorithms out there.
So if you remember nothing else from today, here's your AdaBoost cheat sheet. 1. It's a boosting method that learns from mistakes. 2. It trains weak learners one by one to reduce bias. 3. It cleverly assigns weights to both the data points and the learners. 4. It's super powerful for things like face detection, but be careful with noisy data. And 5. Because it's sequential, you can't run it in parallel to speed things up.
And that kind of brings us to the big idea here. AdaBoost is more than just code. It's a philosophy. It's proof that a systematic, adaptive focus on what went wrong is a direct path to getting smarter. So the question I want to leave you with is this. If this principle works so incredibly well for machines, what could it unlock if we applied it more deliberately in our own lives, in our teams, or in our companies?